Good evening, everyone. I'm Bree Gertler, Deputy Provost and Senior Vice Provost for Academic Affairs and a professor of philosophy here at the University of Virginia. Thank you for joining us for this virtual program on Mysteries of the Cosmos, Science, Philosophy, and the Big Questions. If you have a question during the program, please enter it in the Q&A box at the bottom of your screen. We will try to answer as many questions as we can at the end of the talk. We're recording this event and we'll post it on Lifetime Learning's website in our vodcast library. Visit the website in a week or so, engagement.virginia.edu/learn. Now it's my pleasure to introduce our speaker. Kelsey Johnson is a professor of astronomy at the University of Virginia, an affiliate faculty member in the Department of Religious Studies, and interim associate dean for undergraduate education in the College of Arts and Sciences. She is the past president of the American Astronomical Society and founding director of the award-winning program Dark Skies, Bright Kids, a volunteer-run science outreach group serving elementary schools across Virginia. Professor Johnson has won numerous awards for her research, teaching, and promotion of science literacy. Her TED Talk on the importance of dark skies has more than 2 million views. Kelsey Johnson's new book, Into the Unknown, The Quest to Understand the Mysteries of the Cosmos, has been named one of the top 20 nonfiction books of 2024 by Publishers Weekly. Kelsey, the floor is yours.
Thank you, Bree. I am looking forward to this. This is going to be so much fun. And welcome to everyone to this virtual event. Now, I want to start by saying something that I think everyone knows at this point, because you just heard the introduction from Bree, but I'm an astronomer. And a kind of awkward thing to admit is that when I'm in polite small talk at a gathering and you're exchanging the pleasantries that one normally exchanges, and someone happens to ask why I'm an astronomer, I always actually struggle answering this question because there's this polite small talk answer, which is along the lines of, I find the universe to be fascinating. And then, I'll continue by replying and asking why they went into the profession that they did. But the problem for me is that whenever I'm asked this question, the way I really want to respond when someone asks why I'm an astronomer is I want to ask why they didn't go into astronomy. Because for me, thinking about the big, beautiful existential questions of our universe and our place in it as humans are really at the core of what it means for us to exist on this planet. And so that is where this talk is coming from. So with that, let me share my screen and get the presentation going. What I want to do in this next hour is invite you into a place of really existential curiosity. And for me, I want to note that I'm a scientist, and so therefore you would properly infer that empirical inquiry is important to me, and it is. But empirical inquiry, math, and logic can take us to the outer reaches of modern science. But some of the most vexing questions that have been really perplexing humans for millennia are beyond the reach of these tools. So these big, beautiful existential questions really live, from my perspective, at the intersection of science, philosophy, and theology. So that's where we're headed in this talk, because to my mind, that's where the good stuff is. That's where there's rich conversations and dialogues to be had about what it means to move forward with these questions. Now, before we even get into this perplexing, mind-bending material, I want to assure everyone that you already have an A, because if for no other reason, you have already volunteered to attend a lecture at night for no credit, but also some of you, being the overachievers that you are, already by the end of last semester, if you had pre-registered by that point, had already submitted over 7 pages of questions, which is astounding to me. So despite my best efforts, we are not going to be able to do justice to to all of these questions over the next hour. And in fact, each of the topics we're going to touch on really deserves a lecture all of its own. But we'll do the best we can. If I don't get to your question, and I really do love questions, and this may be a foolhardy move, but I want you to consider it a standing invitation to get coffee with me if or when you are in town in Charlottesville. One, because I love talking about this stuff and nerding out with people who like talking about it too. And also I love coffee. So if you're in town and we don't get to your question, let me know and we can connect. I also want to give you a heads up that at the end of the talk, I'm going to give you some homework. It won't be graded, so you don't need to worry about that. But the homework is related to my 3 goals for this lecture. First, I really hope that by the end of this talk, you are even more curious about the universe. And apparently, given the questions you have pre-submitted, many of you are already bringing a lot of curiosity with you to this presentation. Second, I want you to feel more empowered to think about some of these big, beautiful existential questions that sit at the core of our understanding of the universe. And then finally, I really hope that you learn something that you want to share with someone and pay it forward and maybe instill curiosity in someone else down the road. So with that, I want to start with an observation of mine, which is backed by numerous studies, and it's a little bit sobering. Here it is. My observation is that amid modern life, as we spend nearly all of our time inside and on screens, we are becoming increasingly disconnected from the universe. Now, I don't know if the universe cares, but I would argue that this disconnection from the universe is really to our peril, and collectively leads us to forget that we are part of something much bigger, and there's so much more to learn about it. Now, the thing is, I think most of us go through life and we seem to more or less understand the world of our everyday lives. And our world seems to make sense. But a lot of that is because we are used to it. Things just are. But if we stop to consider how limited and provincial our experiences are in the scope of the universe, and give ourselves permission to think about why things are the way they are, it becomes clear that our understanding of reality is really only skin deep. So here are some of these big fundamental questions about the universe that are beyond our lived experience, and they truly keep me up at night. So I'm going to do an experiment here. I love experiments, and sometimes they work and sometimes they don't. And that's the thing about experiments. So hopefully this experiment will fall on one side of that and not the other. But I want to see if we can make this a little bit of a choose your own adventure. I'm keen to know which of these topics you are most and perhaps least interested in. And we have a poll ready that I hope that we can deploy now. And I'll give you, a few seconds to try to answer these. So these are these big unanswerable questions. Now, the answer to any one of these questions is we don't know. And if I had to pick my favorite, I'm not sure which one I would choose. So this may or may not be a hard choice for you as well. Hopefully you will be interested in at least one of these. If not, this talk will not be nearly as interesting to you as I would like it to be. So I'll give you, another few seconds to finish up your responses, and we'll see where we land. Now, this is really interesting. There's a little bit of a race here going on. And it's interesting to me to see where people are coming in. Wow, we have almost all the respondents now. I don't know if everyone can see the number of respondents at the top of it, but we're over 1,000 at this point. So this is fantastic. We're looking at actual data. So Patrick, who's behind the scenes right now, I hope that you can capture this data for me so I can use it in future talks, because this is fantastic. All right, so I hope that everyone can see how these numbers are coming in. If you can't, Patrick, I hope you have a trick to share it. It looks like where the universe came from is coming in as as the winner, but everything at least got some votes, and that warms my heart because all of these things are really important to me. All right, so I am going to go ahead and move on from this poll. Thank you for letting me know your interests. And we'll go from there, and I'll try to spend more or less time on things depending on where those numbers came in. Okay, so again, as a scientist, I want to stress that I believe in the importance of empirical inquiry. Oh, share results. Can everyone see the results? Hopefully. Yep. So I really do want to stress that I believe in the importance of empirical inquiry. And I think empirical inquiry is essential for us in terms of trying to understand the universe of our lived experience in our everyday lives. Now, I think it's important for us to pursue empirical inquiry as far as it can take us. But there are aspects of the universe that may be outside the limits of empirical inquiry. And we need to have enough intellectual humility to understand what those limitations are and where they live. So as we look at each one of the mysteries here in turn, it's helpful to think about what the limits of empirical inquiry are. So first, sometimes we just need more time. Now, as an example, I want to point out to you that we have only had the two pillars of modern physics, so general relativity and quantum mechanics, for about a century. That's not a lot of time. So for many things in physics and cosmology, we might just need more time to make progress, to do experiments or create technology or develop more theories. So time is something I never want to lose track of, and I never want to forget that we may have advances in the future that we can't possibly even imagine right now. The second category of limitation has to do with our own brains. Now, this I say is cognitive, and the issue here, I think, is that we like to, as humans, we tend to be fairly human-centric, and we like to think of ourselves as being highly intelligent creatures because on Earth, we seem to be the most highly intelligent creatures. But there's something here that's really important to keep in mind, and that is our DNA, and there's a lot of DNA in there, right? But our DNA is only 1.2% different than that of chimpanzees. Now, chimpanzees are super smart, there's no doubt. And I don't know if of the people who are attending, there happen to be any chimpanzee trainers. If there are, please follow up with me after this talk. But I suspect, and I'm willing to be proven wrong on this, but I suspect that you probably could not teach a chimpanzee calculus or thermodynamics or general relativity or quantum mechanics. So by extrapolation, I think it's important for us to keep in mind, what if our intellectual ability were another just 1.2% further advanced? Are there things that we could understand that we can't even come close to understanding now? So this means really in sum that we need to take a big, healthy spoonful of, I would say, some intellectual humility. Right? We may not be the apex of intellectual evolution, and there may be things that we as humans are not capable of understanding and may never be. Now, I'm not saying that that is the case, but I'm saying we need to be open to that as a possibility. That doesn't mean we don't try, because as scientists, we're always going to try to move forward. Now, the third category here, I'm calling fundamental. And here what I mean is we might really hit a truly fundamental wall because we are embedded in and part of the universe and subject to its laws. And no matter how advanced we might become, cognitively or technically, there are things we may, and I want to stress the word may, we may never be able to probe or interact with because it's just outside of our ability to do so in the universe. So science can take us right up to the boundaries of some of the most compelling questions in the universe. Then what? So it turns out when we look at these great mysteries, and these are some of my favorite mysteries, some of them might actually be solvable? So I want to start with a few of the questions that might be answerable in the not too distant future, maybe in a generation or so. We just need more time, right? They're huge mysteries now, but there are advances on the horizon that could lead us there, and we have not hit the limit of empirical inquiry. So first up, let's talk about extraterrestrial life. Who doesn't love talking about extraterrestrial life? Well, actually, don't actually answer that. That was entirely rhetorical, because if you don't, then you should go to another talk. So when we think about extraterrestrial life, I want to point out something about Earth that is incredibly important and suggestive. Now, the problem is, I think, as you all know, there's only one planet in the universe that we know to have life, and we are on it. And a data sample of one is not particularly robust, and we need to be very careful about extrapolating. But with our data sample of one, there are two things we know to be true that put together are entirely remarkable. First, everywhere on Earth that we find water, we find some form of life. Second, it turns out that there are signs life emerged on Earth as soon as it possibly could have. And what I mean by that is, if we rewind to the very early solar system, which was a very dynamic and a very nasty place with giant, planet-sized bodies flying around, not in nice, tidy circular orbits. The surface of the Earth was literally bombarded and resurfaced, possibly over and over and over again. So even if life had gotten going before this period called late heavy bombardment, it probably wouldn't have survived. But we see signs of life almost as soon as late heavy bombardment ended. So if we take that as a data set of one, what it suggests is that when the conditions are right for life to emerge, it's not so hard to do so. We want to be a little bit careful because we have to make a lot of assumptions, but there are real reasons why we might expect there to be lots of extraterrestrial life, even if it's microscopic or primitive. So searches for extraterrestrial life are underway based on what we think we know about life as we know it. And I would actually be willing to make a bet, not a very large bet because I'm not a betting kind of person, but I would be shocked if we don't find some kind of life, however microscopic or primitive, within the next generation or two. I really think the statistics here are on our side. But I also think there is a lot we don't know about life. And moreover, we may actually need to establish a continuum of aliveness. Trying to define life, it turns out, is very hard. It's extremely fraught. And our working definitions of life are very human-centric. And my own belief is that we need to think much more creatively about what life is and what forms life might take. Now, I want to make a quick side note on this slide before we move on to the next mystery, because I think this is kind of alarming and fascinating. And we can certainly dive more into extraterrestrial life question and answer period. But if we work through some numbers and we think about how likely it might be for intelligent life to emerge and to become technologically advanced, we can play around with some toy ideas. And here's a toy idea. So, the Milky Way, the galaxy we live in, is about 10 billion years old, give or take. I'm an astronomer, so we round things off. And if life randomly emerged in the galaxy over this time period, and let's say over this 10 billion years of the, many billions of stars in the galaxy, let's say civilizations emerged on 1,000 times. And we could work through those numbers later if we want. What that means, if we took that as a toy idea to play with, is that a new civilization is popping up roughly every 10 million years or so on average. But if we flip that around, where this gets really interesting to me is that, in other words, the next youngest civilization to us would be something like 10 million years more advanced than we are. So in this scenario, and in really any scenario that we think about advanced extraterrestrial life in the galaxy, we are most likely by far the babies. And if you think about how much further evolved and advanced we might be in 10 million years, if we survive, there is a lot to unpack, and there are big implications for humanity. All right, next mystery. I'm trying to get to the next mystery. Here we go. What about dark matter and dark energy? Now, some of you may not be familiar with these. Certainly, if you're not an astrophysicist, this is not part of your daily life. And I expect most of the audience are not astrophysicists, although there may be a few of you out there. It turns out that we don't know what roughly 95% of the universe is made of. And that's kind of a lot. And when I say we don't know what it's made of, I mean, we really don't know what it's made of. So, everyday matter, air, tables, the chair you're sitting on, stars in the sky, intergalactic material, that's all sort of ordinary matter. That's only 5% of the universe. There are these two other components that we call dark, which is code sort of in astronomy speak for we don't know what it is, but it doesn't appear to interact with light or electromagnetic waves, in other words. So we call it dark. We believe these components exist because we can see how they interact with other aspects of the universe. And in the case of dark matter, we see its existence via gravity. In the case of dark energy, we see the expansion of the universe. The universe is expanding, by the way. I want to make sure everyone knows that. But the expansion of the universe is actually accelerating, which was a paradigm shifting discovery of a couple decades ago. And so we infer some kind of energy has to be causing this acceleration. And this is the dark energy. And so when we add up all of the mass energy of the universe, again, we don't know what 95% of it is. And these are huge questions in modern physics. But just like with extraterrestrial life, there are experiments underway to try to understand these. And we haven't yet reached the limits of empirical inquiry. We just need more time. Now, finally, of these three, I want to get to hidden dimensions, and we may be able to probe these in the coming generation. Now, I know that this probably sounds like science fiction, and I hear you on that, and certainly this is a plot device deployed in science fiction all the time, but there are actually legitimate physical reasons to think that there might be other dimensions beyond the three of space and the one of time that we are familiar with. These could be what's called compactified, which is a great word that means they're curled up so small that we can't even probe them yet with our experiments. Or they could be what we call macroscopic, meaning they're large, potentially infinite dimensions that are outside of our normal dimensions of time and space. Now, again, I realize this sounds like science fiction, but there are actual experiments that can be and are being done to try to test this. The experiments today are fairly unadvanced, but technology is coming along at a rapid pace, and there are ways that we can begin to actually probe the possibility of these extra dimensions. So again, it's not yet completely outside the realm of empirical inquiry. So after those, we're left with a host of questions that might, and I want to stress the word might, never be knowable. And I want to say here, though, I really want to always be cautious to never say never. Some of you may be familiar with the late Arthur C. Clarke. He was a famous futurist and science fiction writer. He was responsible for the 2001 Space Odyssey movies and more. He had three what are called laws, Clarke's three laws, and this is the second of the three laws. And this is always top of mind for me when I'm thinking about possibilities in the universe. What he said was that when a distinguished but elderly scientist states that something is possible, they are almost certainly right. When they state that something is impossible, they are very probably wrong. And so I always want to be very careful to not be a curmudgeonly, calcified senior old scientist and try to hold open possibilities where we can. But when we hit these questions that may be unknowable, the general tactic I think that we want to take is, given what we think we know, what options are on the table? And that's where we're headed with these questions. And let's start with black holes. Black holes are a perennial favorite because they challenge us to contemplate the limits and the possibilities of the universe, and definitely provide excellent plot devices and any number of science fiction stories. Now, what happens inside black holes actually has connections to every single one of the other mysteries in the remainder of this talk. And so there's a lot of crossover here between what we don't know and the universe. But if we try to take stock about what we know about black holes, here's some things that are very interesting. First, when we cross what we think of as the boundary of a black hole, it's called the event horizon. It's the distance from which light can't escape. Time itself becomes imaginary. And when I say it becomes imaginary, I literally mean that in a mathematical sense. So I'm actually going to share an equation with you here, and you don't need to solve it. But sometimes math can actually help our intuition. So in this equation, what I mean by imaginary is that 2gm over rc squared becomes greater than 1. And then 1 minus 1, well, 1 minus something greater than 1 is a negative value. And we have a square root of a negative value, and time itself literally becomes mathematically imaginary. In fact, in many ways, once we cross the boundary of a black hole, time starts to behave like space, and space starts to behave like time. And so if you really want to stay up late at night running your brain in circles, you can try to think through what that would feel like. The next thing we think we know about black holes is that we believe as we just cross that boundary of a black hole, we think our laws of physics as we understand them hold for a while. But as we approach that central, what we call singularity of a black hole, we know that our laws of physics as we understand them don't work. In particular, general relativity and quantum mechanics don't get along, and something has to give. And so we know that we don't know the physics that's happening in the cores of black holes. There are some options on the table, though, and I want to share these with you. And they may seem strange. I'm only going to share a few of them that are actually less strange than some of the ones that are even stranger that are coming out of modern physics. So one possibility that is on the table is that deep inside of a black hole, when a black hole is formed, a baby universe is formed and born on the other side, if you will, of the black hole. In fact, our universe itself is consistent with having been formed in a parent universe that had a baby black hole. So this is a possibility that is on the table. So you can see how this is related to some other aspects of this presentation. Another option on the table is what's called a wormhole. It could be that a black hole is able to connect one region of space-time to a very different region of space-time, sort of giving us a shortcut. Now, I know, again, this sounds like science fiction, but it's not disallowed by general relativity, and it's an option that is still very much on the table. And then finally, it could be like deep down in the center of a black hole, space and time are so stretched and warped that we end up with sort of a topological knot in the actual fabric of space-time. So there's a lot of weirdness here to be explored. The problem, and the reason this sits outside of empirical inquiry, is at least as of today, we know of no way to cross into a black hole and come back out. And so that makes it very hard to report your findings and get them published in a peer-reviewed journal. Now, what about the laws of nature themselves? Now, if memory serves, this is the one that got the fewest votes at the beginning of this talk, so I won't spend a lot of time here. But I do want to make a couple points because I think this is really interesting. We don't know why the universe has the laws that it does. We don't know why we have these laws and not some other laws. We don't know where they're encoded or how they inform the universe about how to behave. We don't know if there is a meta law that determines the laws that we could have in our universe. And is there a meta law that determines the meta law that determines the laws that we could have in our universe? And so when we think about why we have the laws of the universe that we do, we very quickly end up in a philosophical tangle. But I'm going to move on from this because this got the fewest votes, though I'm very happy to talk about it and question and answer later. Now, time. Time is a slippery concept. We interact with it almost continuously, not almost continuously, we do interact with it continuously. And if you have a way to not interact with time continuously, please let me know, because as someone firmly in my middle age, I would very much like to stop that. So we interact with time all the time in our lives, and most of physics is defined with respect to time, but we don't actually understand what it truly is. I would argue that time is perhaps the single concept that we simultaneously have the most exposure to and the least understanding of. Now, part of the problem is that we are embedded in the flow of time, which makes it very hard to examine from an external perspective. And the nature of time, because of this, the nature of time used to be entirely in the realm of philosophy. But modern physics has given us a little bit of insight here, and I want to try to share this with you. These concepts get really abstract because we're going to be thinking about time in a way that I think most people are not used to thinking about time. In fact, I think most people are not used to thinking about time at all. But we're going to think about time here. So I want to start with something we've learned from general relativity. And this may take a minute to get your brain around. So I'm going to use an analogy. And I like to use an analogy of a loaf of raisin bread. And you, being the owner of this raisin bread, you can slice it at whatever angle you want, right? Clearly, hopefully you've all sliced bread at some point in your life. And so this analogy isn't too hard to visualize. Now, this loaf of raisin bread actually represents space-time. Although we're only going to think about 2 dimensions of space, we're going to have to ignore this 3rd dimension of space, because if we don't do that, it's almost impossible to visualize a multi-dimensional loaf of raisin bread unless you're more talented than I am. So we have 2 dimensions of space, which are the face of the bread, right? The slice of the bread. And we have time, which is going along the length of the bread. Each slice in this situation represents now at different locations in a 2-dimensional slice of space for a particular observer. Now, what general relativity tells us is that your slice in this raisin bread will be at a slightly different angle than my now, or my slice in this raisin bread. In other words, my now slice might be in your future. Parts of it might be in your future. Or a raisin in my past slice might actually be in your present. And so, in other words, there is no now, but more than that, it is functionally consistent to think about the entire loaf of raisin bread existing. In other words, the past in some sense still exists. And the flip side of that, in some sense, is that the future already exists. Then we can look at what quantum mechanics tells us, right? The other pillar of modern physics. Now, I realize that this equation looks like it could cause bodily harm. And I will assure you that it also causes emotional and mental harm for physics students around the world. But this is one of the fundamental equations in quantum mechanics. Now, one of the things that quantum mechanics tells us about time is that time isn't even defined at timescales smaller than what we call the Planck time. The Planck time is 10 to the power of negative 43 seconds, roughly. So incredibly small. Below this time scale, time is actually fuzzy and not well defined and may not even be continuous. So quantum mechanics has something to say about time as well. Now, finally, we can also think about time as having a shape, a morphology, and an orientation. So could time have a beginning or an end? And what would that mean? I have often found with my students in class that many people are comfortable thinking about space as being finite, but we're much less comfortable thinking about time as being finite. as having a beginning or an end. And then the next part of this orientation is, why does time appear to have a preferred direction? If you don't perceive time as having a preferred direction, please do let me know, because I would like to follow up with you on this. But as far as I know, everyone I've ever talked to about it perceives time as having a preferred direction, and we have no choice in it. I get to choose whether I'm going to walk to the left or the right or forward or backward, but I don't get any choice about the direction I'm going in time. And this is something very much an unknown in the universe. Now, finally, we're going to come to what is, at least to my mind, one of the most compelling mysteries of them all. And I will say this is one that keeps me up thinking way past normal waking hours, regularly, often. And that is, where did the universe come from? Now, I think that this one got the most votes, and I kind of thought, because this isn't my first rodeo, it might get the first vote. So that's one of the reasons why I saved it till last. We have some issues here, though, that are both philosophical and linguistic. Now, here's one issue. One of the hypotheses on the table is that time itself, as a dimension, came into existence with the universe. If that is true, and time didn't exist before the universe, we get into some linguistic problems. Because if time didn't exist, we can't ask when or what happened before the universe was created, or what caused the universe to be created, because all of those depend on time existing. And so we're very much in murky philosophical territory here. But even if this is an unsettled question about whether time itself came into existence with the universe, we can push our physical understanding back to very early times. How far back can we go? So it turns out, and some of you may find this actually shocking, there are experiments happening on Earth now that can recreate conditions in the early universe, when the universe was 10 to the power of negative 32 seconds old. If you want to pause and think about how incredibly young, how incredibly small 10 to the negative 32 seconds is, I mean, it's beyond human comprehension. And we can recreate those energetics in labs today. But even our theoretical understanding of what could possibly be happening in the universe completely breaks down at this Planck time that we've mentioned before, 10 to the power of negative 43 seconds. Beyond this time, further back toward a time equals zero, if a time equals zero existed, we know that we don't know what's going on. We know that we don't understand the physics. Now, it could be that new modern physics will push beyond this boundary. There are different theories of what's called quantum gravity at play that could help us to understand and push past the Planck time, but they're not on the horizon just yet. Nevertheless, there are some hypotheses in play, and I want to share these with you. As far as I'm concerned, all of these are on the table. Some of them are going to sound crazy, and I think some of them will sound differently crazy to different members of you who are listening for different reasons. But because these are beyond our ability to empirically test them, my argument is generally that we need to keep an open mind and keep all the ideas on the table until we have a reason not to, because it's like pruning off healthy branches on a tree that could still bear fruit. So here are some options on the table being seriously considered as hypotheses for where the universe could have come from. First, there could be a cosmic cycle that alternates between a big crunch and a big bang, and it goes back and forth. This has been a favorite for a long time, and is certainly embedded in many mythologies and cultures around the globe. The problem with this is that right now, dark energy seems to suggest that this option is not as viable as we once thought it was, but I'm not willing to take it off yet because we don't really understand dark energy. Second, and I think this is probably the answer you would get from your friendly physicist on the street, if you were to poll them, I think the most popular answer from a physicist would be the universe came from a quantum fluctuation. Again, this is very much on the table. We can't rule it out, and there are loopholes in quantum mechanics, that allow this to happen. And in particular, one of the great things about quantum mechanics is that the whole notion of causality gets muddied. And so that gives us some breathing room when we're struggling with time having a beginning and whether there could be causation. Now, we talked about this with black holes. It could be that our universe was created from a black hole being created in another universe. In other words, we have a parent universe. And our universe as it exists is not inconsistent with this. And in fact, when we think about what we envision as the Big Bang, in many ways, it looks like the opposite of a creation of a black hole. So this hypothesis is on the table. Brain collisions. Now, please note the spelling of brain. It's not the kind of brain like we have in our heads. This kind of brain is short for membrane. And the idea here is if we could think about our three-dimensional spatial universe as existing in a higher dimensional space, like a membrane. And so brain is short for membrane. And if our universe exists in a multi-dimensional, higher dimensional space, there could be other universes there too, other so-called brains. And if these brains collide, we imagine there would be a whole heck of a lot of energy input into a system. So this is a hypothesis that has been on the table. Now, I want to get to one that I think is probably on everyone's mind, and that is a higher power, right? This is beyond the realm of empirical inquiry, which means we can't prove it and we can't disprove it. And so I think it needs to stay on the table. I do want to offer you a twist on this, though. I think often when many people think about a higher power, often people think about a conventional deity or God from whatever religious background people might have. But there's another option here, and there's a reason I didn't say God, and there's a reason I said higher power. It could be that our universe came from some incredibly advanced, super technologically capable, multidimensional species that's doing a simulation or an experiment, which leads us to the next one, which is that it is a hypothesis on the table that our entire universe is a simulation. There is a whole philosophical school that has been working on this, led by a philosopher named Nick Bostrom. And what Nick Bostrom would argue is that in some sense, statistically, he would argue that it is more likely that our universe is a simulation than a genuine actual physical universe. And so this is a hypothesis, as unsettling as it might be, that is on the table. And then finally, with all of these unsolved mysteries, we only know what we know. And we always have to be mindful of what I think of as a really key bias, and that is availability error or availability bias. We can only think of the solutions that we can think of. What if there are things we're not thinking of? And so always with these unsolved mysteries, I want to leave space for something we haven't thought of yet, right? Let's invoke that intellectual humility and acknowledge that we have probably not thought of every solution that's possible. And let's keep thinking of things and keeping them on the table. Now, here's the thing though. Let's say I could tell you, and I can't, I wish that, well, do I wish that I could? I don't know, that's debatable. But let's say I could tell you which one of these caused the universe to come into being. Your next question, right? Let's say that I could tell you our universe came from a black hole and a parent universe. Your next question might be, well, where did that parent universe come from? And down we go. And so what happens is that we end up fundamentally in a philosophical issue, because even if I could tell you what caused the Big Bang, you might ask what caused the Big Bang, and what caused the Big Bang, and down we go into what is called infinite regression. So different stories have encapsulated this idea of infinite regression in the form of turtles, a stack of turtles all the way down. And this is in reference to Earth being on the back of a turtle, which is in turn on the back of another turtle, and so on, all the way down. And from my perspective, our modern cosmology is not in such a terribly different state. And most days when I find myself frustrated with not being able to make progress on these mysteries, I think about the turtles, and I think If only we could just get one more turtle down. But here we are with infinite regression. Where does that leave us? All of these topics bring us face to face with the limits of science, logic, and in many ways, our own intellectual capacity. But for me, they also connect back to what it means to be human in the universe. And in a very physical, a very real physical sense, I want to remind you that we are all literally made from elements in the universe. And in a very real way, we are actually fluctuations of the universe itself that are sentient. In other words, we are the universe itself made self-aware. And as far as we know, at least today, and you can see back to the slides on extraterrestrial life, we are the only sentient beings in the universe capable of trying to understand the universe, which to me gives us an almost ethical imperative to learn about the universe. And in turn, I would say also learn about ourselves. So here's your homework. Now, hopefully this doesn't catch you off guard because I gave you a preview of it at the beginning of the talk. First, please lean into curiosity. Even if there may not be answers, often I'm challenged as a scientist and when thinking about existential questions, what is the point of thinking about these things if they may not be answerable? And I would argue that curiosity itself has value. It's the only value of curiosity doesn't mean that we are able to answer something or produce something. Curiosity itself is essential and important. So lean into that curiosity, especially when there may not be answers. Second bit of homework, please try to spend some time thinking about the universe. It's so easy to be embedded and taken over by the day-to-day of our lives and, getting dinner on the table and hitting a 5 p.m. deadline. But try to look up from time to time and think about where you are and think about what you're a part of. And then finally, I really hope you learned something tonight that you thought was interesting or curious that you can share with someone, and light a spark of curiosity and instill that in someone else. And then finally, because I know you are all overachievers, after all, you are voluntarily attending a lecture at night for no credit, there is also extra credit. And the extra credit is this: please visit a truly dark night sky. Dark skies have been a touchstone for humanity for millennia. They have connected us to the universe, and they remind us that we are part of something so much bigger than ourselves that is mysterious and beautiful and awe-inspiring. But these dark skies are rapidly disappearing, and within less than a generation, they may be completely gone. So do this soon and put it on your bucket list, and I promise that you won't regret it. With that, I'm very much looking forward to the Q&A section, and I would like to invite Bree back.
Wow. Thank you, Kelsey. That was amazing. I want to say mind blown. We have so many fantastic questions for you. So I'll just jump right in. Here's a question that we got both in advance and another version of it while you were speaking. How, if at all, has your work on cosmology shaped your religious perspective? How do you connect scientific cosmology and theology?
Starting with a light one, huh? Thank you for that question. And as a reminder, right, I'm always open to coffee. So the first thing I want to say is that I try very hard in my teaching, and I will do so again now, to keep my own spiritual beliefs in my pocket. And I do that for a reason, and that is I worry that we are so often actually taught not to think for ourselves and to listen to experts. And I think it's so important for people to listen to themselves. And I never want my students to have what I believe to be true influence what they believe to be true. That being said, what I will offer, instead of completely evading this question, which I promise maybe over coffee, I'll tell you the real answer, is that my own views on religion and spirituality have evolved dramatically over my career. Uh, and I think that that's healthy. And I think it's really important for us to have a life of self-reflection and not get stuck in a way of thinking or in a belief that we may have worked for us at one point in our life. The more I learn about the universe and the more I interact with other knowledgeable people, and the more curious I am and I dive into things, my beliefs have changed. Now they're sort of settling down, and they have sort of settled down over the last decade. So I don't know how much more they will change, but they have changed, and I think that that's really important.
Great, thanks. At one point in your talk, you said time starts to behave like space and space starts to behave like time. And the question said, yikes, what does that mean?
It means in some sense what you might think it means, and that if you think intuitively about what it means for you to move in space, like you right now, I believe probably have a choice about which direction you move in space, but not a choice about which direction you move in time. When you cross the boundary of a black hole, and I'm going to sweep a lot of stuff under the rug here for the sake of brevity. The fabric of space itself, right? We think of space time as an actual, I mean, not literal fabric, but we think of it as a thing that exists even if we can't tangibly interact with it. The fabric of space itself flows into the black hole like a river, and you get stuck in the flow of space just as you are right now stuck in the flow of time. Another way to think about this, and I actually had a slide on this in an earlier version of the talk that I took out for the sake of time. But this is just a super, I'm a nerd, but I think this is a super fun thing that other people might think is fun to know. You may have heard that you can't travel at the speed of light, right? Anything with mass, nothing with mass can travel at the speed of light. And that's sort of true, except for this. That's true only if we're thinking about traveling at the speed of light through space. It turns out that everything, including me and you and your chair, your table, is traveling at the speed of light, but through space-time. What that means, in other words, is that light, which is traveling at the speed of light, because that's why the speed of light is named the speed of light, is only traveling through time. It's only traveling through space. It's not traveling through time. You, who are, more or less sitting still, let's neglect the earth is rotating and stuff like that for now. If you are sitting still, that means that you are only traveling through time and not through space. So right now you are traveling at the speed of light through time. And so time and space start to play off each other. And these are very abstract concepts. But what happens inside of a black hole is they start to get mixed up in a way that's not intuitive because of our lived experience in the realm of the universe where we live.
Great, thanks. Switching gears, what is your favorite science fiction movie and why?
Oh gosh, okay, that's a fun one. Couldn't we have started with that one instead of like my religious beliefs? Oh, I have so many favorite science fiction movies and why. Okay, my very, very first favorite science fiction movie was the movie Contact. Some of you may remember it. It came out in the mid-90s. It's getting a bit dated now. It has a very young Matthew McConaughey in it. That movie, when I first saw it, hit me so hard because it was written by the late Carl Sagan. Some of you may remember Carl. And his intention in writing the book from which the movie was based was to make it as realistic as possible. Everything in that movie was so spot on and so realistic. Okay, up until the point where we actually make contact with extraterrestrial life. And at that point, sorry if that's a spoiler, by the way, spoiler alert, we make contact with extraterrestrial life. And at that point, he extrapolates based on what we think might happen and what might be feasible. But that movie felt so realistic to me that I woke up the next morning after I saw it, expecting there to be headlines about having contacted extraterrestrial life. So that movie will always be special to me because it really, I think, is authentic to the way things are and the way things might unfold. A close second and third to that, though, which are more modern, are Interstellar, which, you know, and for which Hollywood actually consulted with black hole experts to try to understand that physics, and it's just an emotional roller coaster. And Arrival, if you have not seen Arrival, because that gets deep into thinking about the the anthropology of outer space and the linguistics of outer space and how beings might be so different from us that we have linguistic challenges. So those are my top three.
Great. Okay. This is a little more political. What do you think about SpaceX and private citizens going into outer space?
Ooh, that is very political. Let's see if I can answer it in a not political way. I think that space belongs to everyone and space belongs to no one. And for that reason, I think having private citizens go to space in the sense that space belongs to everyone is fine, right? Because going to space can be awe-inspiring and help you understand your place in the universe. And so whatever we do to engage with people to help people feel awe about the universe, to my mind, is on balance a good thing. Where I start to feel some pretty severe cognitive dissonance is with the level of colonial mindset that is being deployed. And I would say, from my perspective as an astronomer and also as a human, my sense is that our abilities and our corporate aspirations are radically outpacing our ethical thinking. And I would much rather have it the other way around. We are racing to space in a way that is almost unmoderated and completely unthoughtful. And I have a lot more to say about that. So let's please go out to coffee and talk about that one.
Great. Okay. Final question. How do you stay motivated thinking about topics like these that so often yield little success? Does it become overwhelming when studying and not necessarily discovering immediate solutions or answers?
Oh, that is such a good question. Oh, how do I answer this fairly and honestly? Part of it is, I would say, it's actually a little bit relieving because you're not expected to get a result and you're not expected to get an answer. And in some sense, you when you think about topics like this, you're given permission to sit and contemplate and think without an expectation of overt monetizable productivity. And I feel like that's something that's being lost. Now, maybe part of it is just how my brain is wired. And, you know, from my earliest memories, I've just always in my core wanted to understand our place in the universe as humans. And maybe in my middle age, I'm coming to terms with the fact that maybe we never will understand our place in the universe as humans. But I don't stop thinking about it. And I think what I would challenge is a notion that the only reason we do things is to be productive. And sometimes I think there's real value in doing things to do them for their own sake and for their own value. At least that's what I try to tell myself when I get mired in these philosophical knots.
Great. Well, Kelsey, thank you so much. I have learned an awful lot, and mostly I have learned how little I know, which is always, I think, a very productive first step. I also want to thank the audience for joining us and for the great questions. And just echoing something that Kelsey said, we had 1,300 participants at one point. We have almost that many still hanging on at 8 o'clock. And you are all overachievers. The Office of Engagement has told me that the people who registered are alumni, they're current UVA students, their parents. This has just been an amazing event. And so thank you everyone for joining us.